Good evening everybody. Welcome back to the diagrams what we are talking about for the different electronic transitions, and basically we are talking something related to the different types of correlations. So, how these correlations basically are helpful in identifying several of these electronic transitions, and we have talked about these in terms of the different Russell-Sanders terms and those particular terms which were involved for all these transitions, and we can identify a particular type of that state such as the corresponding 3F state, what we were just getting by simply handling any vanadium complex in the trivalent state having a corresponding electronic configuration of 3d2. So, if we have two electrons in two different d orbitals, they will interact, and the overall interaction what we are getting is that due to the different term symbols for the orbital angular momentum and the spin angular momentum interactions. So, when we get this particular F term, we know that it has the corresponding 7-fold orbital degeneracy, and how all these states basically, if it is definitely have the 7-fold, and how we will have the corresponding splitting for these degenerate levels, and if they are not degenerate after putting that particular free ion system. So, this is the 3D2 free ion system, and we will place inside a corresponding crystal field. So, how crystal field can basically go for the corresponding splitting of these different states, that we will see for the corresponding correlation diagram what we were just started discussing in our last class, that we have a D2 electronic configuration, and for that we will just definitely we are getting the corresponding states which are 3F, 3P to up to 1S. That means the 7-fold degeneracy to a 1-fold degeneracy in case of 1S system. And these are basically when we put that particular ion, that means the vanadium chloride trivalent state, that vanadium trichloride or any other vanadium compound in +3 state. So, they will basically undergo splitting in an octahedral crystal field. So, the 3F term what is the ground state, it is labeled as red in color. So, that will undergo basically splitting in 3T1G, 3T2G and 3A2G, and these two are having 3-fold orbital degeneracy, and this has 1-fold orbital degeneracy, and apart from their corresponding 3-fold spin degeneracy in all these cases. So, whatever we are getting from the 3F term is that 3A, 3T and another 3 term all will be having the same spin multiplicity, and we will see that if there is some splitting between these 3 levels which were degenerate originally, we can expect the corresponding electronic transition can take place from the ground level to the first excited level to the second excited level. So, that is basically the corresponding correlation diagram what we will be getting for this particular system, where we will have the weak interaction side and the corresponding one as the strong interaction side. So, as we move from left to right, we have the corresponding crystal field strength which is increasing, and at some point we will have a strong interaction, infinitely strong interaction. So, we will have the corresponding interaction will tell us that we have both the 2 electrons into the T2G level. So, these are the corresponding orbital occupancy. So, how this particular orbital occupancy can also give us some of these states, that we can find it out. So, when we are dealing with this 3F states, so we have altogether this particular one where we have, if we count both the orbital and spin degeneracy. So, this is 3 into 3 9, this is again 3 into 3 9. So, 9 plus 9 18 plus 3. So, these will all corresponds to 21 microstates. So, all we know that we have in this D2 configuration we have 45 microstates possible. And out of those 45 microstates, we are having 21 microstates for the ground state term, that is the 3f term. So, in the same fashion we will just count the other microstates also. For this 1D term we have, this is the triplet state and this is the doublet state, since the spin multiplicity is 1. So, altogether we have 5 states, 5 microstates over here. Similarly, here 3 into 3 9 microstates. So, all if we add up to the 1s level, so we will have all 45 microstates possible. So, these are theoretically possible 45 microstates for a D2 electronic configuration. So, if we just try to get the corresponding correlation with that of the strong field case or the infinitesimally strong interaction case, where we have the T2G2 electronic configuration, and in this particular case if we have how many states basically possible out of those, so that we can find it out initially that you have the T2G levels possible. So, if we have the T2G level which is T2G2, and we all know that in T2G case we have the 3 orbitals possible. So, when we have 2 electrons in this T2G level, so the first electron can choose any of the 3 T2G orbitals with the spin basically up. So, we have basically altogether we have the 6 such orbitals available. So, factorial 6 by factorial 2 by factorial 4, altogether 15 microstates possible for this T2G2 configuration. So, this basically gives us some idea that in the strong field case, in the weak field case we have 21 microstates out of these 3f states, but on the right hand side we do not have the corresponding 3f term, but we have the T2G2 configuration, and out of that we have the 15 microstates permissible. Then out of these we have the next higher one. So, which one? Next higher, and then next to next higher level. The next one will be T2G1, EG1, and the next to next higher level would be EG2. So, in this particular case, since the 15 we have counted over here, so we have when one electron in the T2G level and with the 2 spins. So, you have 3 into 2, that means the 6 possibilities. Here, and either of these, the EG with either spin, for the case of EG also, for the next electron we have 2 into 2, that means 4 possibilities. So, altogether we have therefore 6 into 4, that means 24 microstates. And in the last case, again like that of the corresponding permutation of these levels, we will just get the corresponding values like factorial 4 divided by factorial 2 and factorial 2, that means 6 microstates. So, 15 plus 24 is 39 plus 6. So, altogether when we add up on the right hand side, we also have 45 microstates, which is known to us that we have the 45 possible microstates in the corresponding free ion case. So, if we just correlate now those 45 microstates from the left to the right of those states, basically how we get this, the number of electrons and the total number of ways, basically what we are finding out from the general relationship like n, which is the total number of ways we can distribute these microstates. So, it is the total number of ways we can distribute, which is factorial 2y divided by factorial x into 2y minus x, where x is the number of electrons, where x is the number of electrons and y is equal to number of orbitals. So, we get all these levels starting from these values. So, how we get that? So, we will have now those states basically. So, the T2G2 what we have calculated out, that it corresponds to, therefore, altogether 15 microstates. The next one will correspond to basically 24. So, largest number of microstates will be here, and the top one, the EG2 configuration, will have 6 microstates. So, now out of these basically 15 microstates, how we can distribute this? Because if we look at on the left, so one particular combination would be this one, where we will have a triplet spin degeneracy as well as triplet orbital degeneracy, giving rise to 3 into 3 altogether 9 microstates. Similarly, the singlet spin and the triplet orbital give rise to 3 possibilities, and here also 2 and here also 1. So, 9 plus 3 12, 12 plus 2 14 plus 1 15. So, that basically accounts basically the all 15 microstates what we have calculated just now from the possibilities rule for a T2G2 configuration. Similarly, we can distribute among the different triplet states and the corresponding spin multiplicity, though this will be 9 and this is also 9. So, 9 plus 9 we have 18 plus 3 is 21 plus 3 24. So, that also accounts 24 microstates, and similarly in the last case we have 3 into 1 is 3, possibility 3, then 2 5 and then 1 6. So, this is our corresponding 6 possibilities. So, looking at these corresponding levels which we are getting when we place the particular free ion terms within the corresponding interaction field which is present in the octahedral geometry, that the corresponding levels from left to right would be all same. So, whenever we have a corresponding 3 T1G level, on the right hand side we must have the corresponding 3 T1G level. But the other singlet levels will definitely will not come from the 3F level, but will come from 1D level. So, other two will come from 1D and one other will come from 1G. So, all these levels 3 plus 2 5, 6, 7, 8, 9, 10, 11 this particular states. So, these 11 states and altogether 45 microstates should be there, as well as we have this on the right hand side. So, just now the next thing is that how we can correlate this, how the energy of this 3 T1G state will change with the change in the corresponding field strength in the corresponding octahedral crystal field splitting. So, this will go down basically, that means this particular level will be stabilized as we move from left to right. Similarly, this energy of this particular state will go up and will have the correlation with the T2G EG state. Then the third one will have correlation with the EG2 state and will have the 3 A2G configuration. So, we just if we just push one electron from the corresponding levels, that means the T2G level, that one electron will, if we push there, will go to this particular electronic configuration, and the corresponding correlated level is 3 T2G. Similarly, the next electron when goes to the EG level, so both of them are in the EG level. So, the corresponding triplet state which is of one-fold orbital degeneracy will have the correlated level as that of our 3A2G. So, this basically gives us the corresponding simplified correlation diagram, and from there we just basically derive the corresponding diagram which is known as our Tanabe-Sugano diagram. So, this is the basic groundwork from the deriving the thing from the Orgel diagram to this particular diagram, that how we correlate this and quantitatively we can find out the corresponding transitions, and if we precisely find out the corresponding separation, we will be able to calculate out the amount of energy due to the transition from say 3T1G to 3T2G or 3T1G to 3A2G. So, that basically gives us how we just manipulate the corresponding axis. So, in the terms of the corresponding diagram, the Tanabe-Sugano diagram will look like differently compared to this simplified correlation diagram, and how we can draw this particular Tanabe-Sugano diagram, that we will see in our next slide for this particular occupancy. So, these are the corresponding occupancy for the T2G2 level, this is T2G1 EG1 and this is EG2 occupancy. So, in the real complexes we will have this particular range basically for these interactions, neither we have the free ion state or we cannot have the corresponding very strong interactions. So, in between we have always these things. So, how we get these particular types of these Tanabe-Sugano diagrams, that we will see that this we have just seen that this is in our hand for the corresponding correlation diagram, and how we change this. So, one thing we can go for that, basically this particular change in energy we will just put it as a corresponding horizontal line. So, definitely the Tanabe-Sugano diagram will be first thing what we will just characterize it having some horizontal axis, which is very important. So, all such diagrams for the different dn electronic configurations, if it is a corresponding Tanabe-Sugano diagram, it must have a corresponding horizontal axis representing the corresponding ground state energy from the weak field case to the strong field case. So, in the horizontal axis we will just put the corresponding crystal field strength. So, we will put here the corresponding crystal field strength as we move from left to right. So, in the horizontal axis something we will put in terms of the corresponding delta octahedron. So, delta octahedron will be there, which is our corresponding octahedral crystal field splitting in this particular geometry. So, octahedral crystal field splitting will be there for this delta O value, and this can be nicely changed to this particular one. So, in actual sense this is not only the delta 0, but we will introduce some other parameter which is known as B. So, on this axis, on x axis we will just be placing delta 0 by B, and this B is nothing but one particular constant which is known as the corresponding Raka parameter. Which is the corresponding Raka parameter, which basically measures the repulsion between the terms, repulsion between the terms of same multiplicity. So, that we have seen in case of the Orgel diagram, that how one particular term is basically deviating. So, if there is repulsion, so we will not have some crossover for that particular term, and we just basically try to deviate the corresponding thing. That means, if we have the 3 T1G term, one is originating from P and another is originating from F. So, these two terms basically of the same spin multiplicity, they will try to repulse each other, and we have the corresponding repulsion, we can find it out in the diagram. So, this particular axis is given by the delta 0 by B, and which is accounted for its corresponding increasing field strength. So, if we push this 3 T1G level from this black line to the dotted red line by moving from here to there. So, we get this as the typical horizontal axis, which is defined as 3 T1G. Since it is originating from the 3F term, it will be labeled within bracket as 3 T1G F. So, once we move this from here, so our 3 T1G term, which is again correlating with the 3F term, will go off further. So, this is the second line. So, bold line is the next one, the 3 T1G. And the third one is, which is much more steeper, is the entire thing we are moving in the anti-clockwise direction. So, the other one, the 3A2G, so 3A2G is moving further. So, this angle, basically angle is changing. So, basically if we put all these angles constant, so once we move this much angle for moving it to the horizontal axis, the other angles will also move like this. So, basically we get out of this 3F the 3 values. So, it would be now nice to see that if we, wherever we are, if we are at the value of 10 or value of 20 or value of 30, depending upon the corresponding increasing crystal field strength. So, that will definitely gives us some idea that where will we have the corresponding transition from this level to this level, or from this to this, or from this to this. So, we do not have to worry about the corresponding level for the 3T1GF depending upon the corresponding crystal field strength. So, we had made it horizontal. So, that is, this has the corresponding advantage of looking at the corresponding transition from any such point. Since it is a quantitative measure of the corresponding transition energy in the electronic spectrum. So, wherever we are, if we are here or at 20 or at 30, we will be able to calculate out quantitatively the corresponding energy separation between the 3T1GF and 3T2G term. So, in this particular axis, which was originally as the energy axis, now in the vertical axis. So, what will be there in the vertical axis in Tanabe Sugano diagram, which is important to know. So, it will have corresponding energy again in terms of B or in units of B. So, this is basically the corresponding energy of the excited states, energy of the corresponding excited states, which is above the ground state. So, in terms of that, the E values are measured how much it is different compared to the corresponding ground state energy. So, the relative state all the time will have the corresponding relative state, and with respect to that relative ground state will all measure the corresponding transitions for these cases. So, the next one we had the 1D case. So, this is also having some axis from 0 to 60. So, we will have the 1D case, and 1D we have the corresponding splitted level, which is shown as the dotted line. So, dotted line are those states where we have a different spin multiplicity originating from a corresponding singlet state, because we have the ground state as the triplet state. So, we should expect the corresponding transitions only to the corresponding triplet states. So, from the ground state we have the ground state as well as two other excited states. Similarly, from the 3p level, this was shown here in the correlation diagram as the bold black line. Here also this 3p, it was there as the corresponding horizontal line typically, but now since the change in the corresponding axis, it will also going steeply up and it is try to deviate. So, there will be repulsion here. So, it is not a typical straight line. So, like in the Orgel diagram, we have the corresponding curvature in the 3 T1GP term, which is above this other corresponding 3 T2G term. So, in between what we are getting apart from the corresponding 3 level, one is the ground and other 2 excited level, we basically introduce the term which is not 3 T2G, but it is 3 T1G, since it is originating from 3P level. So, but this is another possible excited state where we can see that the excitation or the transition can take place for a corresponding D2 electronic configuration. So, altogether we will have 1, 2 and 3 transitions. So, in the electronic spectrum for all these vanadium compounds in the trivalent state, we should theoretically get 3 basic transitions in the Tanabe-Sugano diagram. So, how we get these values and how we can correlate those values, that we can see next. So, when we have a different type of spin multiplicity, say for chromium 2, if we have a corresponding spin multiplicity equal to 4, which is different from the vanadium case where the spin multiplicity was 3. So, from the spin selection rules, we can only expect that intense transitions can only take place between the ground state 4A2 and the excited states of 4T2, 4T1 and other 4T1 excited states if it is originating from other excited levels. So, the spin thing, that means the restriction from the spin level, that if we have a corresponding multiplicity of 4, so we should only consider the excited states having the same spin multiplicity. The other transitions are therefore spin forbidden. Just now we have seen in case of vanadium case also. Therefore, we would expect to see 3 DD transitions on the absorption spectrum. So, likewise in the vanadium case, in the case of chromium also, we have this is the ground state and these 3 are the 3 excited levels. So, we should nicely be level the 3 excited levels, and this is one transition, this is second transition and this is third transition from 4A2 to 4T1. So, in DD transitions we are basically getting 3 absorption. So, that was not so easy to find out, but if we look only the orbital contribution. So, the corresponding term values are important and the corresponding correlation diagram in terms of the Tanabe-Sugano is important to know the exact number of those DD transitions. So, if we can sketch these transitions in order of increasing energy, that means if we take the different levels in Tanabe-Sugano diagram and then we go for transition from one particular level to the other, we will see that the spectrum what we get as we would expect it for only the DD transitions in a D3 octahedral complex. So, order of increasing levels, that means we take the ground state, then the first excited level, then the second excited level and the third excited level, that will tell us immediately where our corresponding new 1 band position, the corresponding new 2 band position and the new 3 band position will take place. So, this is the corresponding example for this electronic configuration, and we have the transitions, and if we record it in corresponding lambda values and we see that close to 1100 nanometer we have the lowest possible transition, that means the from 4A2 to 4T2 transition. So, this particular transition basically corresponds to the first band. Then we have the second band close to 800 nanometer and which is a broad one and which has some other small solder type of absorption here there, which is not so sharp like the other one. So, we have some broad spectrum. The feature of this is very broad, which is for the second one, which is the transition for 4A2 to 4T1 level. So, this is 4A2 to 4T1. And lastly, the third one from 4A2 to 4T1. So, this is the corresponding band position. So, as we move from the low energy, which is towards the red side, this is the low energy transition, this is the medium energy transition, and this is the corresponding high energy transition. So, these three transitions can be nicely correlated once we know the corresponding diagram, and experimentally what we measure, this is the experimentally determined spectrum for the corresponding ion, and it is placed in the corresponding octahedral geometry, and that basically correlates the corresponding values in terms of its energy. And if we just look at the corresponding epsilon values, we see the corresponding epsilon values are also increasing. So, high energy transition is much more probable compared to the low energy transitions. As we move towards more higher energy towards the UV side, we will find that again the possibility of getting the corresponding charge transfer transitions can take place, where the corresponding epsilon values are pretty high. So, from these three spin allowed transitions, so we are having all three transitions which we are getting, these are all spin allowed transitions, and we expect 3 DD bands appear in the spectrum. So, theoretically also, if we know the corresponding electronic configuration in the octahedral crystal field, immediately we can predict the number of DD bands what we can experimentally get if we measure the corresponding compound and its solution in any such salt, and we measure it in solution and we get that particular transitions. And in addition to these, basically as we move, because when we make a solution say of 10 to the minus 3 molar concentration, we get this particular thing. So, when we basically get the 10 to the minus 3 molar concentration, if we are lucky enough in the range of the corresponding epsilon values, we get these two transitions with this concentration, then we dilute it further 10 times to get a 10 to the minus 4 molar concentration, where we get this particular transition, and if possible the other one which is in the charge transfer region. So, in addition to these three, basically we can have some more transition which can be assigned as the corresponding ligand to metal charge transfer bands, because ligands will play some important role where we have the free metal levels possible, where we can see the corresponding charge transfer bands on the left hand side of this. That means it is below 350 nanometer in this particular range of the electronic spectrum. So, how we can find out, because we have to measure the corresponding electronic transitions we have seen theoretically. So, basically this diagram what we have, so we can nicely predict the transitions, and experimentally what we are measuring the corresponding electronic spectrum. So, before going to measure the corresponding electronic spectrum, we see that it is possible to have the quantitative determination of these different levels and their corresponding transitions, and if we calculate it out, that means if we have the theoretical calculations, we do expect at least the corresponding band positions where these bands can appear. So, in the spectrum we basically see that these are the things if we can have. So, we have the three positions. So, that nicely tells us that how we can get these three maximum values for these three transitions, and the epsilon we can calculate it out. We have to calculate out from the absorbance values. So, if we have the different absorbance values, we can calculate out the corresponding epsilon. So, in case of the D2 electronic configuration, the spectrum what we get basically is this. So, 1 is in the range of, this has been shown in a reverse order, basically the low energy is in the left and high energy on the right, for the sake of convenience for writing the corresponding centimeter inverse scale from 5000 to 35,000, from very low value of the centimeter inverse scale to the high value, because in most of these cases and most of these calculations we calculate these values for the different transitions, the new 1 band and the new 2 band, in terms of the corresponding centimeter inverse, like that of our FTIR spectrum. The infrared spectroscopy also we find the corresponding energy values which do appear in the IR region with these values. So, if we extend these basic values for the very low energy, this particular site, more low energy site, basically this particular range, we call it as the corresponding NIR region. So, there are several spectrophotometers available where we can have the corresponding range, say we can scan the entire range, say 2600 nanometer to say 180 nanometer. So, we will have all these ranges to appear nicely within the electronic spectrum. So, this is basically that UV visible range, then we have the visible range, and then also we have this NIR range. So, most of these spectrophotometers, so in one single spectrophotometer we can have all these three, we can measure together. So, we basically go for the corresponding NIR measurements also using some UV visible spectrophotometer, and on the left basically we have the range which can be measured for its bond stretching frequencies, which is in the FTIR values. So, these are electronics transitions and these are the corresponding vibrational spectroscopy in the range of the corresponding FTIR. So, the NIR tell what we can get is sometimes these are also very weak, but can have some significant informations, and if we are able to get those values we can have some good correlation for the different electronic structures of the system, that means the corresponding metal complexes. So, we have these two transitions for the vanadium 3 compound, and what we see then that the corresponding Tanabe Sugano diagram what we had earlier, that this is the corresponding Tanabe Sugano diagram, which basically predicts that now the corresponding spin allowed transitions, which is nu 1, nu 2 and nu 3. So, these are the 3 spin allowed transitions, but what we see that in the electronic spectrum, what we see that we have 2 bands. So, 2 band positions what we see in the electronic spectrum, and when we analyze the Tanabe Sugano diagram critically, we find that we have the corresponding transitions like this. So, we should have these 3 transitions. The nu 1 is the low energy one, nu 2 is the medium energy, and nu 3 is the highest possible energy transition for the spin allowed transitions from 3 T1GF to 3 A2G. So, what we basically get that these are the corresponding level for these transitions, and if we are not getting the corresponding high energy transitions, so that is basically we can consider it missing and we can go inside the corresponding charge transfer bands. So, this particular configuration can have also help us to identify the other configurations for this corresponding electronic transitions in the particular case if we have the D1 configuration. So, that D1 configuration we can have to find out that since we know that in this case the 2D is the ground state, and what we have seen in case of the Orgel diagram. So, what we have seen earlier that we have seen for these 2, basically we have seen earlier that we had two orgel diagrams, and we have this basically this crossing thing for a particular term. It can be D or F term. So, these particular terms basically are getting splitted when we have the different crystal field strength, and now from there we just basically what we have seen, that we know now that what we have to do, that we have to do this particular term, basically this particular energy level for this particular state have to move to the horizontal axis. So, Tanabe-Sugano diagram basically in all these cases. So, if we want to have it as a corresponding TS diagram from the orgel diagram, we just have to move it for the corresponding horizontal axis. So, if we had earlier these two splitting for this 2D level, say 2 T2G and 2 EG level for that, now we just move this one there and this slope can go further for the other level. So, basically from this the entire figure we are moving from here to there. So, that gives us the corresponding value for this configuration for the 2D level for D1 electronic configuration, and we basically get for the corresponding spectrum for the titanium compound, the titanium 3 plus, that one particular electronic transitions we can have from 2 T2G to 2 EG level. So, nicely we can write it down that the corresponding band what we are getting for hexac or titanium compound also, where the corresponding electronic spectrum we expect to get at 430 nanometer. So, this 430 nanometer band is basically due to the corresponding transition from 2 T2G to 2 EG level, and depending upon the corresponding crystal field strength. So, this can be in terms of the corresponding B units, that means delta O by B also, that we have the corresponding field strength. So, depending upon the field strength we have the corresponding separation in the energy. So, as we go from left to right, the field strength is increasing and our energy for the corresponding transition is also increasing. Similarly, we have the corresponding hole formalism, that means the equivalent configuration and the state for the D9 configuration. With respect to the D1, we have the same ground state term which is 2D, but the splitting what we have seen in case of orgel diagram, that one is on the left hand side and other is on the right hand side. So, what we have here is that here now we have the 2 TEG state is the ground state and 2 T2G state is the excited state. So, the ground state term is changed for D9 case compared to the D9 case, but we have the different energy for it go for the corresponding D9 case, which is for the copper 2. So, any copper 2 compound having this particular state can show at least one strong band for this particular transition from 2EG to 2T2G state. So, this basically tells us also that for a simple coordination compound, whether we are making a corresponding compound of titanium, whether we are making a corresponding compound of vanadium, or say a corresponding compound with a 3D9 electronic configuration, that means a corresponding compound of copper in +2 oxidation state, that means the corresponding complex in cupric state. So, one particular DD band which is most characteristic one apart from the other charge transfer transitions or other sort of transitions, that can be very well characterized for its corresponding DD transitions, but the states involved for those copper compounds, say the tetraamine copper 2 ion, can show the corresponding band due to the transition from 2 EG level to T2G level. So, the next one would be the higher one that we are discussing very much on this. Basically, we already know we should be all the time we should be able to predict it for the corresponding D2 electronic configuration. What we are seeing in case of the vanadium compound, that we have the 3 excited levels and we have labeled these as the corresponding ground state and the 3 other excited state. So, once we know it the corresponding vanadium compound for these, we should have some good idea for its whole formalism, its whole equivalent, which is the D8 electronic configuration, which is the most common one. What we see for all these cases is for the corresponding nickel compound. So, if we have the nickel one, so in this particular case, since this particular 3p level, the only difference is that we do not have this particular crossover region for this, because this T1 and this 2 T1, this also basically is repelling, and we do not have this particular crossover over here. So, this 3-1 will repel the and go up basically, and we cannot have the corresponding configuration for these. So, we have the 3 other levels for this D8 electronic configuration. So, with this particular level we have the 3A, but this 3A2 is now the ground state, because everything is now reversed like that of D1 with respect to D9. Here our 3A2 level is the ground level. So, this cannot be the excited one. So, this is the ground level. Then we have the 3T2 level, then we have the 3T2 level and the 3T1 level, this particular one, this which was the ground state for D2 electronic configuration. So, this is the 3T1, and then the 3T1 level which is coming for the other one. So, since now we have the 3T1 term which is originating from the 3F is the excited level, as well as the 3P term which is also coming from this 3P term which is in the excited state. That is why these two are repelling each other. But in case of D2 electronic configuration, we have this crossover, because this crossover is permitted, because these two levels are different. One is 3T1 and another is 3A2. They are not having the same orbital multiplicity. If they are of same orbital multiplicity, they will not cross to each other, they will repel each other. This is the case where here we see that this 3T1 and this 3T1 both are repelling each other. So, the corresponding correlation diagram for the Tanabe Sugano form is that is a little bit different compared to our D2 diagram. But for the nickel also very simple one, if we dissolve nickel in water we get the corresponding green solution. But basically when we measure the corresponding electronic spectrum, we basically measure the corresponding 3 transitions. This is the first transition, this is the second transition, and this is the third transition. So, very nicely in any common textbook we find it, and occasionally we ask this also, how we can identify the 3 basic DD transitions for a nickel 2 plus ion in solution. It can be the nickel 2 in water environment, that means all 6 water molecules surrounding the nickel 2 plus ion, or it can be 6 ammonia molecules surrounding the nickel center. They will have difference in the energy values only, but both of these 2 ions can show 3 very specific transitions related to this Tanabe-Sugano diagram. Then we have the D3 one, this already we have little bit we have discussed with regard to that of our spin multiplicity. This is the quadruple spin multiplicity for this, that means 4-fold degeneracy of the spin level. We have this one for 3 unpaired electrons. So, the S value is equal to 3 and to half is 3 by 2. So, spin multiplicity will be equal to 4. So, like our D8 configuration, we have 4A2 is the ground state. Here we have 3A2 is the ground state, here also 4A2 is the ground state, then the next T2 is the excited state, then T1 like this also, and this T1 is. So, these 2 configurations, these 2 diagrams with relation to the Tanabe-Sugano will have some similarity. You see that this is basically for D3 and D8, that again we have 3 basic transitions. What we can see for D8 in case of nickel 2 ion is also true for the D3 case, where we have these same 3 transitions are possible, but the level for the states which are responsible for these transitions are different. Here we have the states originating from 3f, here it is originating from 4f, excited state is also here 3p, but in this particular case it is 4p. So, these are for these 5 electronic configurations. Then we can have this particular thing that we can just other one, the corresponding charge transfer transitions what we have seen in case of the corresponding ligand to metal. So, when we have the corresponding transitions in originating from the metal, the transition of an electron from T2G pi and the Eg sigma level or the T1 level, T1U level, which is pi star and sigma star, those transitions basically due to the availability of the orbitals from the ligand side, which is all of antibonding time. So, these transitions will arise from the pi acceptor ligands, and the metals are willing to donate the electrons in the orbitals which are of ligand character. That means, they are of antibonding nature and they are of high energy, and the metal field levels can donate those electrons for charge transfer transitions. So, whatever electronic spectrum we are seeing just now, so beyond 400 nanometer we can have certain this sort of transitions also possible, where we can see that this particular transitions can take place involving metal orbitals as the donor orbitals and ligand orbitals as the corresponding acceptor orbitals. So, we have the T2G level which are of pi character and Eg level which are of sigma star level. So, electron can go from the T2G and the Eg, that means the sigma star level also can be possible. So, what we have here that we have the 3 in say octahedral symmetry, we have the 3 T2G level which are in between the corresponding Cartesian axis facing the ligands. So, they are of pi type, and also we have the Eg level. So, Eg levels are basically the corresponding sigma star type, so this particular sigma star level is there. So, if we are talking about metal to ligand charge transfer transition, so metal orbitals, so these two are our corresponding metal orbitals, and these metal orbitals are basically utilized for something that depending upon the number of electrons available. If it is a D3 case, so this T2G, that means the pi type of orbitals is available to some of these ligand type orbitals. So, some of these ligand type orbitals will be somewhere here. So, these ligand type orbitals will be there. These are the corresponding ligand acceptor levels. So, these ligand acceptor levels will be available there, and if these are originating from the corresponding ligand which is of level symmetry level of T1U, and these T1U type of these orbitals can be for this particular symmetry level which are basically the acceptor level. So, in the next step basically what we find that this particular electronic charge can move from this T2G level to the T1U level. So, what we see this simply this transition is from T2G level to T1U level, and this T1U level, since it is the corresponding ligand type, it can be both, that means it can be of pi star type or sigma star type, depending upon the corresponding orbitals which are directly facing the corresponding ligand metal orbitals. So, if they are directly facing the metal orbitals, they will be of sigma type, and if they are in between, they are also pi type. So, that we will discuss in our next class, that how this particular type, that means whether it is a pi type or pi acceptor type of ligand or a sigma donor type of ligand which is having some sigma star orbital available, can accept the electron density from this T2G level. So, we will have this T2G to T1U type of transition, and also we will see that if these levels are also filled. So, if we have one electron like this, that means for 6 plus 2 8 electrons in case of the nickel 2 plus, we can have this particular Eg type, that means Eg level which is of the sigma star type, can also be utilized for the transition to the T1U level. So, all these levels, how these energies can change, basically we will see for this metal to ligand charge transfer transition, how characteristic they are and how we can utilize these bands for analytically establishing the nature of the corresponding metal complex. Thank you very much.